Welcome back to Head Sparsh. Today we are looking at LeetCode 2095, delete the middle node of a linked list. So let's just jump right into the question. We are given a head of a linked list. So let's create a linked list for now. So in the function we will be given this head of a linked list. When we need to delete the middle node and return the head of the modified linked list. So we can even delete the middle node from is this list itself, basically this list itself, or if we want we can also create another list, but it is better that we can create it delete it from this list itself, so that we are not using any additional space complexity. So now how it is saying the middle node of a linked list is size n is the n by 2th node from the start using zero based indexing, where x denotes the largest integer less than or equal to x. So now here you are seeing we have 4 nodes, 1, 2, 3 and 4. So 4 by 2 is basically 2. If you can even see, they have given an example, 4 by 2 is basically 2. So we need to delete the node at position 2. So this was 0, this was 1 and this was 2. So what we need to do here is we need to delete this node. So basically this node should point to this, and we need to return the head itself, this. And then let's say if the values present inside this are 1, 2, 3 and 4, our answer, like the head which we are returning, it will be basically like 1, 2 and 4. This is the head which we have returned here. So they have also given us with some examples that for n equal to 1, that if there is a single node only. So for this node, the middle node is 0. 1 divided by 2, we need to take the lower bound element. So let's say if this is the head which is given to us, then we need to delete this head itself. So for this one, we might need to do a special edge case handling, where let's say if heads next do not exist, basically we can say is equal to null pointer, we'll just return null pointer. But for all of the other elements, let's say for size 2, 3, 4, for 4 we have seen here. For just size 2, I'll just create it quickly. Let's say this is head, this is 1 and 2. For size 2, 2 by 2 is 1. So we need to return what we'll do. 2 by 2 is 1, and that means that we need to delete this second node. So basically 1 will now point to null pointer. So our answer will become head will point to only 1, which is now pointing to null pointer. Now let's quickly just look into one example which is also given by LeetCode itself. So here we can see we are given 7 nodes, 0, 1, 2, 3, 4, 5, 6, like total 7 nodes, 0th based indexing. Now they already have highlighted that we are this is the middle node and this is what we need to delete. So what a person can thought in an interview, let's just like think from an interview perspective too, because from the previous examples this is quite clear. So from an interview perspective, what a person can think that okay, how will I determine which is the middle node? What a person can do, this is given to me as head, I'll just traverse this linked list once. So head will point to head next, like we are just going to make a count that okay, this is value 1, this is 2, 3, this is what is the size of the linked list, 6 and 7. So we are able to find that there are total of 7 elements in the linked list, and we will see what is 7 divided by 2. 7 divided by 2 is equal to 3.5, but we need to take the lower bound of this, and hence the answer will become 3. So in a zero based indexing, because it is given that we need to use zero based indexing while deleting, we are going to delete this specific 7 from here. So what it will demonstrate the interviewer is that you traverse the linked list once. You have traversed the linked list once, and now while coming back, like we will again start from the head. Like we'll see head equal to 0, then we'll see heads next, like current pointer as 1, we see current pointer as 2. Now we know next current pointers next will be pointing to 3, and 3 is what we need to delete. So what we'll do here is we'll just write current pointer next equal to current pointers next. So current pointer next was 7. So now we are just modifying that current pointers next will now be pointing to current pointer next, which was 7, and that 7 next was 1. So we are now directly pointing 4 will point to 1. So and then our resulting linked list will look like, I'll just create this quickly, 1 3 4 1 2 and 6. So this will be our resulting linked list, and this is a head. So now the interviewer will say that you have used two passes, one for finding out how many elements there are, and second for how many elements we need to delete now. So can we even try to do it in single pass? So let's say if we want to do it in single pass, there is a very easy, like standard approach where we basically use slow and fast pointer. So what we usually do is on the first node itself, we basically for the first node, we just make it point slow as well as fast pointer here, and now we'll just move slow pointer by 1 position, but fast pointer will move by 2 positions. So in this case, while the fast pointer reaches the end of the linked list, slow pointer have exactly reached the middle of the linked list. So let's just take this, I'll just move this below. Now let's just understand it with the above example itself. I'll just erase these values, 1 minute. Yeah, so now you can say slow is this, fast is also this. Slow will move by 1 position, so slow now reaches here, so slow is pointing here, but fast traverse 2 positions, so 1 3 and then 4. Fast is here. Similarly, we'll move it further ahead. Slow will point here, and fast was originally at 4. Fast will point here. Similarly, slow will move again 1 position, and fast will again move 2 positions. Now when we are trying to move fast 2 positions ahead, we see that 6 is pointing to null, and null is not defined. So we'll just stop our iteration here. So what will happen in this slow fast pointer technique is that we'll see that slow is exactly pointing to the node which needs to be deleted. But this is what we cannot, like we cannot basically identify the solution from here. Like we cannot reach a solution from here because we need the previous node to point to the next node. Now from slow, we have the next node, but we don't know that which node, like the previous 4's next points to 1, 7's next will not point to 2. So what we are going to do here is we are just going with a very small optimization which we can like come up with, so that we don't need to maintain any third pointer. So what I am going to do is that I have already told you that for if a linked list have only a single node, we'll just return null pointer because that single node itself we need to delete. But let's say if the linked list have more than one nodes, basically two nodes or more, there will always be slow pointer will always point to head, but fast pointer, what we are going to do, fast pointer we are going to start from slow's next. So slow's next will always exist, and that next will always exist, like it could be either be null pointer or any pointer instead. So now how are we going to traverse? We are basically now traversing in the same fashion only. Slow will first move 1 point ahead, slow reaches here, fast reaches 2 point ahead, fast again slow will reach 1 point ahead, and fast will reach 2 points ahead. Now here we see fast next is also again not defined, this is null. So fast next is obviously null. So now what we know, the slow pointer is actually pointing to the node which needs to point to slow's next what we have written before. So this slow next will point to slow next. So this is what just remove this seventh element from the linked list. This is now gone, and this is obviously what we wanted. So with a very slight modification, instead of using 3 pointers, we are now with 2 pointers itself. And here we can see that we are traversing only once, traversing the list only once, as well as we are also not using any space complexity. So space complexity will be O of 1, and for time complexity we know that we are obviously are traversing the linked list of size n, thus time complexity will be of size O of n. So here we have seen that okay, this is the linked list which have 7 nodes, which is odd. Let's just quickly see an example where a linked list is having even number of nodes. So for this linked list, I'll just quickly mark out. So basically 4 divided by 2 is 2, and we need to delete this instead. So now what we have learned from the past is that slow will point to head and fast will point here. Now what we see, that fast next is present, but fast next and next is null. So fast can move one step ahead. So what we are going to do, we will make slow point to 2 and fast will point to null. So slow is exactly pointing to a node which needs to point the node which is getting deleted, its next node basically. So again here if we are going to write slow next equal to slow next, that means 2 instead of pointing to 3, it will directly point to 4, and the resulting linked list will become 1, 2 and 4, and this is the head, and we are just going to return this head itself, and hence we are reaching the answer. So let's just quickly take a look at the solution, how we are going to write the solution. So what we are seeing here is, like I've written heads next if it don't exist. Basically heads next, when will it not exist? Let's say a linked list will have a head node, like single node, and it is pointing to null pointer. So for a single node, its next don't exist. We are going to return null pointer itself, because 1 divided by 2 is equal to 0, and we need to delete this 0. This is at position 0, this node itself, and hence the linked list will, like after deletion, the answer will become null pointer. So for 0th, like for single node, we have handled this separately. Now for the second part, what we are going to see, we are seeing slow is pointing to head and fast is pointing to heads next next. Similarly, how we have done here, slow was pointing to next and fast was pointing to heads next next. So now this is clear. Now what we are seeing, that fast pointer should not be a null pointer and fast pointers next should also be not be a null pointer. And why are we checking these two conditions? Let's say if fast is now at null pointer, fast is at null pointer, then fast cannot move ahead. Similarly, let's say fast is at a node which next is a null pointer, then again null pointers next is what, it is not at all defined. So we have kept this, maintained this condition here, that fast pointer and then fast pointer next should at least exist. And what we are going to do, we are just moving slow pointer with one node ahead and fast pointer is moving two nodes ahead. And what we have seen, slow pointers next, this is what we need to actually set everywhere. This is what we have seen everywhere, that slow next, this was the actual slow which reached this slows next, we have pointing to slows next next, and hence we can just return the head here and we'll be sorted with our answer. The time complexity and space complexity, as mentioned before, time complexity is O of n as we are traversing the whole linked list. Space complexity is O of 1 as we are not at all using any space like this. Slow pointer and fast pointer is O of 2 single space which we have used, nothing else from our side. So that was all for today's video. Please do like, share and subscribe for more such engaging videos. Thank you.